So there's one thing that I want to point out on the course website that I forgot to mention on day one is a big part of this course is that you're able to find and read and comprehend and understand technical documentation. This starts right from the beginning of the course with setting up your TCP socket servers. I don't give you much guidance. Like if I have some time in later lectures, I'll show you a little bit, and I'll show you a quick one today. But you might not see a TCP socket server example in your language of choice. So setting up that TCP server, that is the first thing where you're expected to find the documentation in your language, fire up that socket server, and get that running. On Monday, I gave just a very brief explanation of a good way to do that in Python and in JavaScript. Today, my example will be in Scala, and I'll show you a little bit of code. But if I don't hit the language that you're using, I might not show a Java example. I probably won't show a Go example if that's your language of choice. You're probably not going to see an example. You are expected to find that and figure that out. I will not walk you through every little step of how to write the code for this class. This goes doubly so for your project. When you get to your project, I'm not going to show you barely any of the libraries that are out there available. I'll show probably just one stack towards the end of the semester, and it's going to be after you've hopefully completed most of your project anyway. So for your project, you are definitely expected, which is part of the project, part of the idea of the project. I want you to be able to do that because honestly, that's what you'll be doing your entire career. If you're going to be a software engineer, there's a few people, you'll have some senior devs, but their time is valuable too, who will show you things. But for the most part, it's you having a problem, going out, finding the solution, if that's a library or a framework, reading the documentation, figuring out how it works, and then writing the software to do that. That's what you need to be doing. When you get to these 300 and 400 level classes, if you haven't already seen this, we're expecting you to do more of that. Instead of showing you, like in 115, 116, 220, 250, we'll be like, this is the library we're using for this problem. Here's how to use it. We'll walk you through that. 312, we're not doing that. Other higher level courses, we're not doing that. Because that is explicitly something that we need you to be able to do by the time you graduate. So we have these designed into courses where you do have to find your own, read documentation, find your own libraries and everything. A quick reminder, I do have the Discord still open. I'm watching it on my phone. If you want to go in the Discord lecture channel and ask questions during lecture, I'll be watching that. And with that, any questions before we get into content? I did slideshow before. That automatically advances my slides. I want full screen. All right, let's talk about HTTP and where we are and how we got here to HTTP. So last lecture, we very briefly talked about the protocols that the internet uses, mainly IP, which is the internet. Everything that's communicated over the internet uses the internet protocol. That is the protocol of the internet. It's very aptly named. They did a really good job naming that one. And then TCP, which gives us a way to communicate reliably over the internet, where the internet itself is a very unreliable protocol. We have drop packets. That's a thing that we just live with on the internet. That happens. It will always happen. And with TCP, those drop packets can be invisible to us. You can drop a packet. TCP is going to request a resend. You get the resend, and then once all the packets are there, they're reassembled by TCP, and then they're given to your program saying, here's your data that somebody sent you. And if there's some drop packets, you won't even notice. You might have to wait a few more milliseconds to get your data. You won't even notice a drop packet happen. That's the way we like it. That's what TCP does for us. TCP also adds the idea of port number. And to send a message to your specific program, you need the combination of your TCP and IP, your internet address, your IP address, and your TCP port number to be able to send something to a specific machine. So what happens once we have information at our machine? Well, that's when we get to the stuff we care about. This course is focused on the HTTP headers down. What are we actually going to do now that we're able to reliably communicate over the internet? That's where our focus is. And when a packet is sent over the internet, it's going to look something like this, especially the packets that we'll use for this course. If you pry open some wires of the internet and take a look at the packets going through, our packets are going to look like this. There's going to be some IP headers, like we saw in the last lecture, that very strict organization of bits to be able to indicate which information is encoded in that header. And then the first content, the first bytes of the IP packet, of the body of the IP packet, will be more headers, TCP headers. The TCP headers are going to have things like the port number and sequence numbers to be able to let TCP do its things and have a reliable protocol. And the first bytes below the TCP headers are going to be our HTTP headers. This is the stuff that we're going to start coding. This is the stuff you have to code and work with in your homework assignments. And then the content of the HTTP headers, which could include even more protocols. Over HTTP, we might speak more languages with more protocols, with more headers. We can add even more to this stack. This is a very simplified view of what's called the network stack and the layers of a network. I won't go into detail of the layers. We're going to live right here in the application layer of the network stack. If you want to know more about the other ones, I very briefly advertised at the end of last lecture. Modern Networking Concepts is the course for you if you want to know about all the network architecture. Everything from that course basically handles from TCP up. We're going to handle from HTTP down. Yeah. Oh. All right, HTTP is an application layer protocol. That means our application is interested in this information. Yo.
Just a quick question. So I think you mentioned like the port is like TCP. So if I had like a site that was like 127.0.0.1 and then the port number was 8,000, that 8,000 would be like a TCP like port?
Yep, exactly.
So it's like a sorry.
And no, because I had a slide where I wanted to talk about exactly that, and I think it was this slide actually. So I want to go in depth on that and answer your question. Actually, no, I know where it was. I know where it is. It's way up here. I'll talk about it when I get to this slide. I'll talk about that in depth. Yeah, what's up?
So once we finish this project, will we be using the same TCP socket server, the same socket server that we built for the rest of the class? Or like
Yes. So the TCP socket server and the Docker setup that you're setting up for homework 1, you're going to use that for all 4 homework assignments. So the idea is that you'll keep building on, the homework assignments are slightly disjointed, but there is a lot of overlap at the same time. So the idea is that you'll build one server with all of the features of all 4 homework assignments on it. But if you stumble on one homework assignment, depending on what the objective is, you could still do the next one. Potentially, you like things like parsing HTTP requests, though, you're going to have to do for every single homework assignment. So if you never do that, you're going to have a tough time getting through the course. Yeah. It has fallbacks. Like, for example, if you drop a packet during the 3-way handshake, it's, the best it can do is just retry. So if it doesn't hear from, there are timeouts involved. And if it doesn't hear from the other side for a while, it's going to just try again. But nothing's 100%. If the machine it's talking to completely goes down, for example, it's going to give up eventually. For our purposes, in normal circumstances, we're going to take it as a guarantee that TCP is going to get our data there. Because, barring like solar flares and quantum fluctuations and stuff like that, we're not going to worry about that in this class. For this class, we're going to assume TCP is 100%. HTTP, what we're going to use is, I put that almost there. There must be some really weird case, some weird situation where somebody's using HTTP not over TCP. So then I edited my slide and put an almost there just to qualify it a little bit. But always sounds good. You need a reliable protocol for HTTP, and TCP is that protocol. The alternative would be UDP, if you've heard of that. I won't talk about that in this course, but it's a way to use the internet protocol and just keep the unreliability, which isn't something we want. We don't want to lose even one bit of data, much less an entire packet. Because then the way we build web apps, we just can't do the things we want to do at that point. UDP is only used for things like video conferencing. Like I would assume Zoom uses it. I know Skype did. Because if you lose a packet, you don't want to rewind the video, go back to that packet, and then jump ahead. You just want the live feed. But like something like Twitch streaming doesn't do that. Twitch streaming uses TCP, but I'm getting sidetracked because you can live with like a few second delay in Twitch. But only when it's two-way communication, you want UDP. So HTTP, just like all of our other protocols, there's no magic here. It's just an agreed upon set of rules. It's a slightly different approach than we saw with IP, where IP was like the first few bits will represent this, the next handful of bits will represent this, et cetera, et cetera. HTTP is a little different where it's more textual based. We're going to look for new lines, and new lines are going to separate data, and space characters and colons. We're going to have all these delimiters, and we're going to do string parsing to get the data that we want. But it is still the same way. We have an agreed upon set of rules to specify exactly how we're going to communicate data. So if the sender agrees upon these rules and formats their HTTP requests and responses exactly according to the protocol, then on the other end, we can write code that parses according to the protocol and get all of the information that we need. And as long as everybody's using HTTP correctly, then we can properly communicate over the internet. Our parsers are written the same way as our formatters, and we can get that information communicated no matter what we want to communicate. Yeah. For the headers, yeah. Yeah, and we'll get into all that. And in the request responses, this is how we communicate everything over the internet. Nope, not everything over the internet. Web apps. Even then, I don't know where to draw the line, but everything we're going to do in this course is going to be HTTP. Nope, I can't even say that. You know what? I'm just not going to say anything because we do WebSockets later. It's not over HTTP. All right. So a web server is software that speaks HTTP over TCP. So our web server agrees to this protocol. It's going to be, of course, the server side of the protocol, and it's going to handle requests. And it was my last slide. I missed that one. Where I first want to mention request response protocol. So HTTP is a request response protocol. A client, which is in most cases your web browser, a web browser is going to send a request to a web server. The web server is going to parse that request, figure out what's being requested, handle that request, and then send back an HTTP response back to the client. So we have this client-server protocol, and that's some terminology that will last throughout this entire course. Client, think your laptop, your phone, your browser. Server is going to be whatever software is handling HTTP requests and sending back responses, which is all of your homework code, all of your project code. That's the server. And then you can use your client. You can open up your browser to test your server once your server is running. But client-server protocol, request-response protocol. That's what HTTP is. And more terminology, front end, back end. I know all the terms that I want to introduce. I forget where I have them all in the slide, so that's why I'm looking at the slides. Front end. This is, if you've done any web development in a course at least, like in 199 where we do a little bit, this is what you've seen. In 115 we do a little bit of back end too, so that's a bad example. But the coding you did in 199, if you took that here, that was front end development. HTML, CSS, JavaScript. That's all front-end web development. This is what runs in the browser, and that's what, in this course, we're not really concerned about too much. The back end is anything that runs on the server, things that are not running in the client's browser, that's not running client-side. This is code that's not exposed to the client at all. So anybody accessing your web app does not have access, as long as you have proper security measures, does not have access to your server code or your server, anything that's running on the server. They do have your entire front end though. The very first thing when somebody goes to your website, they're going to send an HTTP request for the HTML. It's going to say, hey, web server, usually at the path / you just go to the domain name itself. It's going to request the root HTML. Your server is going to say, here's your HTML. Send that back to the browser. Browser is going to parse through that HTML, and it's going to see, oh man, this HTML requires this CSS file, a couple of JavaScript files, a handful of images, and it's going to make more requests, separate requests. You don't request a website in one request, in several requests. Request each extra piece of content. So there's going to be an HTTP request for the CSS, an HTTP request for the JavaScript, an HTTP request for each image. A lot of more HTTP requests are going to be made to the server, and even some requests to other servers if you have external links. The web server is going to handle each of those requests separately, send all of that information back in HTTP responses, and then once the browser has all of what we call the static content that it needs to render the page, it's going to do exactly that and render the page, run all the JavaScript, apply all the CSS, and display this web page for you to see in your browser. So all of that, HTML, CSS, JavaScript, any multimedia, that is literally downloaded onto the user's machine and then running. So when you go to a web page, you're literally downloading their code. You're downloading and running their JavaScript code. So you can think of the security implications of that. We're actually running someone else's code on our machines when we go to a website. And JavaScript, luckily, is designed to handle that. Yeah. Yeah, oh yeah. You download YouTube videos too. Yep. That's why you have websites that, if you go download YouTube or whatever they call it, ripping YouTube videos or whatever, there are websites that'll download that for you in an MP4. You do download the YouTube videos, but they're not in MP4 format. They're in YouTube's format, what the formats that they're using. So those websites that you download YouTube is just converting that to an MP4 and then giving you the file. But yeah, you absolutely download it and run it. You download their video player, you download the content, the videos, and then it plays all in your browser, all self-contained in your browser. And then deletes it. Or caches it. If you go back to that same video, maybe it'll load a little faster, but yeah, deletes it and then downloads it again in some cases. And this is why, to expand on that, this is why ad blockers work. Google has a lot of smart people working there, yet ad blockers still work on YouTube. It's because we're downloading everything and then running it on our machines. So once it's out of their hands, there's really not much they can do to stop us from running an ad blocker. And that when we do get to the front-end lectures, just my 2 front-end lectures, that is what I like to focus on is, the fact that the client can mess with your websites. They can change anything because they're literally downloading and then running it. And we'll break some websites when we get to those lectures. I always have fun doing it. Yeah, because it's part of the video, just the way they do that. Wait, I thought ad blockers do work on Twitch, don't they? But possible. So maybe they just invested more time in countermeasures. I'm not sure. I don't know. I don't know. I paid for, Turbo, I think. I paid for that a long time ago, so I haven't seen an ad. I haven't thought about it. So, any other questions? No one in Discord? All right. So HTTP requests, there are a handful of types of requests. I only put a few of them here. There are more than this. But these are the ones that we'll focus on. Mostly get and post. That's what we'll be doing for the better part of this course. We may get into put, delete, and head. These are things that I want to add to the course, but I haven't added yet. So maybe later in a later assignment, I will have these. They do have their place in web app design. And it's just a matter of if I can find room in the course for them. I think I can. But anyway, we'll definitely focus on get and post. A HTTP GET request is, as it sounds, again, aptly named, is when a client wants to get information from the server. It's going to make a request for some information, and the server is going to serve up that information. A GET request usually only contains headers, should only contain headers. If it contains a body, then somebody's not using GET requests, right? And this is what happens whenever you click a link, whenever you download an image, you're sending a GET request to the server, rather your browser is on your behalf, sending a GET request to the server is responding with the HTML, the CSS, whatever static content is being served. And then post requests is when you want to send data, or when your client wants to send data to the server. So when there's some information that somebody wants to upload an image, somebody wants to make a post, post a comment or anything, that's going to be a post request. And this is going to have headers and a body. So there's going to be a body, which is the actual content of the request. which isn't needed for GET requests when you're just getting information, but when you're sending information, we do that through the body of a request. And these look like, 2 slides ahead of myself. To access any information on the internet, we're going to use what's called a URL. I'm sure you've heard of these. You've definitely used them, throughout your lives. But let's break down what a URL is and what the parts of a URL are. So this is like if you go to google.com, that's a URL. A lot of the parts of the URL that you see here are kind of hidden in that or implied. But let's break this down and see what the entire structure of a URL is. So first, we start with the protocol. For our purposes, most of the time this will be HTTP. But if you go to your hard drive and you double click like an HTML file, and then you look at the URL in your browser, it's going to start with a file protocol because that's just a file that you open on your machine. You could use FTP. If you go anywhere on the internet, you're going to see HTTPS because you're going to be encrypted. We won't worry about encryption until way later in the semester, so we're going to be HTTP for quite a while before we get to HTTPS. But the protocol is first, then the host. This can either be the IP address or the domain name of the server you want to access. So if you type in buffalo.edu, that's perfectly valid. It just indicates to the DNS, your DNS code, hey, run this code, access the DNS server, the DNS, and get the IP address for this domain. If you type in the IP address directly, you get to skip a step and just make that request directly. But the host, either by IP address or domain name, maybe. So the question is it faster to type the IP address other than the domain name? Maybe. Certainly, on the order of nanoseconds or so, it will be faster. But most common sites that you visit are going to be cached. So you're just going to have to look that up locally. It's just going to be a database lookup. It'll go, or potentially just a memory lookup. It'll be very quick. If you haven't gone to that domain name before, then you do have the DNS request that has to be resolved, which, it's one more request over the internet. Again, not something that'll be noticeable though. Unless you're really looking to optimize, if you have like a bot or something that's going to a lot of different domain names, then maybe, but not enough that we'd want to worry about it much. Then the port number, so the host and then :port number for the TCP port. And this is how, this is where I want to answer that question from before. This is how information is going to make it to your server. The IP and the TCP are so important in the URL. The IP address, like we talked about last time, this is how the routers of the internet are going to get this information to your machine. To your machine that's connected to the internet. The routers take this IP address and say, this packet is for this IP address, gets it to your machine. At that point, we still need to get it to your process, and that's where the port number comes in. So your operating system is going to take all these IP packets and start assembling them together, realizing they're TCP packets, assembling them together, getting the entire message, all the sequence numbers, everything, got the data. At that point, it's going to look at the port number and say, which process currently owns this port number? And when you start your and each process can only have, each port number can only have one process attached to it. When you start your server, you're going to have to specify which port you're going to run that on. And if another process, and then your code is going to ask the operating system, yo, I want that port. If another process is already using that port, is already listening for internet TCP traffic over that port, your operating system is going to say, port already in use, you can't use that port, somebody else is already using that. For this class, for development, I find that happens most often when you yourself are already using that port. You have another instance of your web server running, you try to spin up another one, port already in use. If you see that, you're probably the culprit. So keep that in mind whenever you see port already in use. If you can't figure out the problem, the easiest way is just to change the port you're using, use a different port. But this is how your operating system realizes that this web traffic is for your specific process, and then it can send the information to your process, which is your running software. And at that point, the data is in our hands. From the path onward, that's in our hands, and we need to think about how to process that. Yeah. It doesn't really have significance. You're absolutely right on that. So the servers on the network, when you have a bunch of servers on a network, you have to name each server so you can route traffic to it internally, so we don't have to remember like a bunch of numbers or something. Or when there are a bunch of servers connected to a network, when the internet and web pages first started coming around, companies, organizations would name their server that hosts their website www. That would be the name of that server. So you go to www, the name of the server, or the subdomain, which usually maps directly to server name, www.buffalo.edu. That would be on buffalo.edu's network and the server named www. These days, that's the server people want to access, so we just have that as the default server now. If you just access our domain name, we're going to be like, this is probably for the website. Let's route them to the web server. And then nobody has to be exposed to the name of the web server anymore. But that used to be the thing. And usually www will redirect to just the regular domain name these days. So people, if you do type www, it still works. If the website is set up to do that, which most websites are. I stopped doing that personally just because I'm like, we don't have to do this anymore, do we? But the amount of ports, the protocol, I believe there's a cap of 65,000, I believe. And I think that's specified by the protocol. I could be wrong on that. You might want to double check me. But there is, I believe 65,000 is, or whatever 2 to the, whatever power of 2 is closest to 65,000. I forget my powers of 2 out further than a few significant figures. The path, any other questions, by the way? The path, the next part, so we're going to have the host, port, and / the path. If the path is blank, then it's a request for just the path /, which we'll call the root path. This is going to specify the specific resource being requested. And this is something that you will have to parse on your end. When you get a request, you have the protocol, the host, the port, that got that information to your server. Now that it's at your server, you have to care about the path. What specifically are they requesting? And this is code that you have to write. For this path, host this. For this path, host this. For this path, host this. Query string and fragment, these are both optional. These are going to give us more control over what's being requested. The query string is going to add more parameters and key value pairs to specify what the user wants. For example, if you want to search DuckDuckGo for web development and you want to do an image search, this is what the query is going to be. If you go to DuckDuckGo and punch in that search, when you get to the search results page, go to the URL. You can click on that URL. Sometimes it shortens it, but if you click on it, it usually shows you all of the parameters. Depending on your browser, your browser will hide a lot of stuff from you. Or cut and paste if it doesn't show you still. Cut and paste the browser into like a text document, the URL, and then you'll see all the parameters. But you'll see when you make a web search, what that's doing is modifying the URL with a query string to give you the request that you want. And then on the server side, it looks at the query string to figure out what you're searching, and then serves your search results based on that query string. So the actual URL itself is changing based on what you're searching and what your search parameters are. And you can add all kinds of things. You can have the language. If you play around with all the parameters on your search engine, you'll get a long query string with all those, with all those options. What does port forwarding and port triggering do? Port triggering, I'm actually not familiar with that term, so I apologize for that. Port forwarding is kind of goes to what I was saying earlier. When you have a lot of servers on a network, when you get web traffic, you have to figure out what to do with that. And usually there's one server that's handling the web traffic, so we're going to forward that information over to that server. So if we get a request on ports 80, did I cover that yet? If I get a request on port 80 or 443, the top level router of my network, I'm going to have it forward that traffic to my web server. So that's called port forwarding. If I got a request for a specific port and I have a network that's more than one machine sharing the same IP address, then I want to forward that traffic to that specific server. If you're, this is common for games if you want to, which well, I guess I can't really assume that. But if you want to play a game that does network play, sometimes you have to forward the port for that game to your machine. So you have one router in your house that's connected to the internet, and that router has an IP address. And then all the devices connected to that router in your home share that IP address. So when you get a request for this game, that router doesn't know where that is supposed to go. When somebody tries to connect to your game or when you host a game, your router in your house doesn't know what to do with that. So you have to log into your router and forward traffic on this port, the port that the game developers chose for that specific game. Say forward any information on that port to my machine so I can get that information. And then your machine is connected to that game. And if you have two people in the same household who want to both play that game networked over the internet, you can't do that because you can't forward that port to both machines, for example. Port trigger, I'll have to look that one up. I don't know what that one is.
They're usually next to each other in the router website, so it's like port forward and it's like port trigger. So
Okay. Maybe it's, I'm just completely guessing here, but maybe it's a more dynamic way of port forwarding. Possibly, I don't know, I'll be interested in that.
I never configured my tap server when I was in high school, so.
I've used a lot of port forwarding, but port triggering is just something I've never had a need for, so I never had to learn it. What do we start, 10, 20? So 11, 10, 15 minutes. And then fragment is used for, it's still, the 20 minutes between classes is still throwing me off because everything, I mean, we've been doing it for a while, but still, like, when does this class end is a question I'm always asking myself. It used to just end when the minute hand was on 50. So the fragment likewise gives you a little more navigation options. It's almost exclusively used for navigation. So if you want to go to a specific part of a page, for example, on Wikipedia, you can link to a specific section of that page. And for PDFs, like, do I want to do an example of this? Sure. I'm halfway there already. Like a PDF, if I want to give a link, ooh, do I remember how to do this? If I want to give a link to a specific page of a PDF, no, I don't remember the syntax. No, that's a failure anyway. But there is syntax to be able to do that, to link to a specific page in a PDF, specific sections of a page. You can use the fragment for that to link to something. So if you're sharing some information with somebody, it's on this huge Wikipedia article, and there's one specific part of that article you want to link. You can link to that using the fragment. And if you click on the navigation at the top of a Wikipedia page, you have the table of contents. You click on one of those. What that actually does is changes your URL to have that fragment in it. So at the table of contents, click the section you want to link, copy that URL, then send that to someone. It'll link them directly to that section of that page. So they don't have to scroll down. You don't have to be like, go to this link and scroll down to this section. You don't have to do that. You can just give them a direct link. Okay, so now let's finally look at some HTTP requests. This is what they're going to look like. They'll be more complicated. They'll have more headers. But this is roughly what they're going to look like when you start parsing these things. This is the format of information you'll have to parse. And I should have mentioned, it's on my slide in one of the first slides, but I'm just giving a very quick overview of HTTP. We're going to go in depth in a lot of these topics in later lectures. So if this is going fast and you're wondering how you're going to code all this, don't worry. We have a lot more time to talk about HTTP. But I just want to give an overview today of what's going on. So an HTTP request is going to be composed of three parts. The request line, I want to make sure I called that the wrong thing before, so I just want to double check there. The request line, which is going to have some very useful information. The request method, for our purposes right now, whether this is a GET or a POST request. The path, which tells you how you have to handle this, what is being asked for, what's being requested here. And the HTTP version number. For our purposes in this class, this will always be HTTP/1.1. So if you don't want to think about the HTTP version number too much, don't worry about it. You can, for the homework assignments, you can safely, I'm hesitant to say this, but you can safely ignore that piece of information. But the request method and the path you definitely need. These three pieces of information will be separated by spaces, and spaces are not allowed in either of these three pieces of information, excuse me. So your first task is to get the first line separated by space, grab the first two values, and figure out what the user is requesting. So when you get one of these, that's your first task. Next will be any number of header fields, which are key value pairs. Each key value pair is on a separate line, and the key and value are separated by a colon. You're going to have any number of these that you'll have to parse through, and I highly, strongly recommend and encourage you to write code during homework 1 that parses all of your headers. Get your request line, parse all of your headers, and get all of these in a key value data structure for your language, a dictionary, a map, whatever you have in your language to store key value pairs. Get all of the headers in that key value store, and never write code that parses headers or thinks about headers again. You just go to your data structure, say, give me the value for this header, does this header exist, etc. Write that code early. I see so many students on later homeworks who still haven't written that code, and they're really frustrated trying to do their assignment because they're still writing hacky code to parse headers each time they need a new header, and it distracts them from actually doing the new stuff for that homework assignment. Write that early. Get that early. And then the body. There will be a blank line separating the headers and the body. So you're looking for this blank line. Read the first line, look for this blank line. Everything in between is headers that you can parse and put in your key value store. And then everything after that blank line is going to be the actual content of the request, which is optional. If it's a GET request, there should be no body. If it's a POST request, there should be a body. If there's a body, there are going to be two headers that are mandatory. The content length, which tells you how many bytes of data are in the body of the request, which is very important to let you know how many bytes of data you should read from the TCP socket for this request, and the type of that data. This is a JSON string, so the type is going to be application/JSON. If it's plain text, that'll be text/plain. If it's HTML, it'll be text/HTML, etc. And we'll talk about content type, which is a MIME type. We'll talk about that in a later lecture in detail. You know what? I can just say that for everything in this lecture, though. Talk about all this in detail later. So those are these are sample requests that you're going to see. And then the host name, I didn't mention this, but every request will have the host name of that served up the original content. First goes to parse these requests. Response. HTTP responses are going to be in almost the same exact format. So there's one real format that we have to learn to speak HTTP, whether it's a request that we're parsing or a response that we're sending, writing and sending. They're very similar. The response is almost always going to have a body. So when you send your responses, content length and content type are going to be required headers. You have to have those headers in your responses. So if somebody's requesting your HTML, you're going to send a response, the content length of the HTML, content type, text HTML, and the actual HTML itself in the body of the request. The one big difference is that instead of the request line, we're going to replace that with a status line indicating the status of the response. So here, a little bit different format, but mostly the same. We're going to start with the HTTP version for all of your HTTP responses, HTTP/1.1, perfectly fine. We're not going to change that throughout the course. We're not going to, there are later protocols. We're going to stick with this one for this class. Then the response code, which is a 3-digit code indicating some information about this response, what happened with this response, and then a human readable status code. So 200 is the status code for OK, that means everything was fine. We're going to put human readable text after that so humans can don't have to memorize their HTTP response codes to figure out what's going on with this. This is the only place where spaces are allowed. Since it's the third value, we're not too concerned. You just look for the first two spaces for the information here. Everything after the second space is that response text. You can have spaces there. Everything else follows the same format as requests. Few response codes. 200, okay. This is the one that you'll experience the most. Usually you'll be in a browser and you'll just be seeing the content that you requested, so you don't have to think about 200s too much from the user end. And most of your responses will be 200 in this course too on your server side. 301 means that whatever the user requested has moved, and you're going to redirect them to a new URL. Not modified means if you have this file stored in cache, just use the one that's cached. Nothing's changed since the timestamp that you sent me. There are caching headers. If you look at that header and say this hasn't changed since your last modified date from your headers, just use the one on your hard drive in cache. Forbidden, you don't have access to that page. Not found, this is where we start getting into the ones that you've seen. These are the ones where something went wrong and you're not seeing the content that you requested. You're seeing some sort of error message. If whatever you requested isn't there for whatever reason, you're going to see that 404. And then 500, this is the scariest one for developers. This is the one that gives us nightmares. That means something went wrong on the server. That the user did everything they were supposed to do, and then the server had something wrong. Like if you went to Autolab before I uploaded the roster. That's me doing something wrong. I didn't upload the roster yet. So you got a 500 error, which should be a 403, but we can update that at some point. But 500 means something went wrong with that server. Okay, last slide at least. I do want to get to my example. And HTTP is a stateless protocol, meaning every time you handle a request, you handle it in complete isolation. You don't get a request and look at some history. Did this user request something else beforehand? Who is this? Let's see. This is their IP address. Let me look up our past dialogue. No, you get a request. You get an HTTP request. Your server handles that request, sends a response, gets another request, handles that response. So for example, when you have a web page that has HTML, CSS, JavaScript, images, each one of those requests for each piece of content is handled in complete isolation. So somebody requests the HTML, you send the HTML, you don't have any code that's going to say an HTTP, the protocol, doesn't have any concept of, okay, we should probably expect a request for the CSS, JavaScript, and images for this page. No, you just forget about it, you send that request back, and surprise, you get a request for the CSS. Whoa, another request? You send the CSS, forget about it. You get another request. Whoa, somebody wants the JavaScript. You handle that request. Everything's handled in complete isolation. And then the browser will stitch everything together and give you the illusion that that was one continuous experience. Often we do want state, we do want that. So what we do is add cookies and tokens, or tokens inside of cookies. And the user will send us a token, which we'll look up in a database, figure out who it is, and then give them personalized information. But that's not part of the HTTP protocol. That's something we have to add kind of artificially after our HTTP requests are parsed. Okay, so if we go to our browser console, if you haven't played around with this, I recommend getting used to this real quick. There's a lot of really good information in here. Some information just to play around with, but especially for this course, for developing, you'll want to spend quite a bit of time in here. And if you come to office hours with the problem, this is one of the first things I do is open up the browser console. It tells you all kinds of information that's going on. To open this, it depends on your browser. In most browsers, though, you right-click and go to Inspect Element. If you're using Safari, you do have to enable this. You have to go pretty deep in the settings, enable developer mode, and unlock that feature for whatever reason. Most browsers, you can right-click and just go to it right away. Or you might have to go into Developer or Tools to get this open, or just do the keyboard shortcut. I forget what they are for each browser. What I want to do right now is go to the Network tab and then refresh the page. What that's going to do is show me all of the HTTP requests that were made to load this page. So we can see a lot of these were cached, and we just got not modified. And I can see all of the information for this request, the URL that was requested, the method, the status code of the response, the IP address and port of the server, all of the headers, well, those are response headers, all of the headers for the request, all of the headers for the response, and the body of the response. And the browser's doing a lot of parsing and displaying this information in a nice, neat manner for me. But if I want to see like the raw headers, it's going to be in that format that we saw: key, colon, value, and then the status line at the top. So we can see lots of information. We can see how many requests it took just to get this one site loaded. Lots. If you go to any modern site, this one's pretty light. I have a pretty simple page here, but lots will be loaded. And finally, 1 minute, we can do this. I can't make this bigger, but this is an example of a Scala web server. This doesn't do much at all, but I am setting up my TCP socket server. If you're using Scala, I guess you can watch the video and take a look at this example. The important thing I want to highlight here is that I'm running this on port 8002. When I get a request, I'm going to convert it to a UTF string, print it to the screen, and then send back an HTTP response which just says hello. So I have this server already running. So I'm going to go to a special host name called localhost, which means this machine. Don't leave the machine. Port 8002. I want to have my console open. And I can see that I got made a request, got the response with these headers. The response was just hello. And if I go into my console, I can see the request that I got. I can see the exact format of that request. I got a request with a request line, a bunch of headers, and then no body because this is a GET request. Your first goal in writing your code is to get to this point where you can just see the requests that were made. The client, you can just use your browser. You can also write client code if you want to test like that, but you can just run your TCP socket server, open it on a certain port, go to your web browser, and go to that port and see if you can get the HTTP request printed out in your browser, just so you can see that everything is working. Once you get to that point, you know you have your TCP socket server set up properly, then you can start parsing some HTTP. And with that, have a good long weekend. I'll see everyone Wednesday.